So good evening and welcome back. If you've been with us before, we're excited to bring you another virtual star party. And tonight we'll be exploring galaxies far, far away. Our presenters tonight are Dr. Mikkel Perry and Richard Stember, and we are all NASA Solar System ambassadors. NASA's Solar System Ambassador program is run by the Jet Propulsion Laboratory in Pasadena, and the program trains about 1,000 volunteers throughout the country to inform the program about NASA missions, the science and technology. Richard has a Bachelor of Science in Chemistry from the State University of New York. He owns and operates a company that develops software for scientists, and he's also an avid amateur astronomer, and he'll be operating our telescopes tonight. In 2014, he founded Science Heads to share his love of science and astronomy with the public, and he serves today as its executive director. Science Heads is a nonprofit organization whose mission is to promote and support STEM education and science literacy. Mikkel has her master's and PhD in astronomy from the California Institute of Technology. And before retiring, she designed spectroscopy instrumentation for the Palomar Observatory. She's now focusing on demystifying science and math for children and adults at outreach events like tonight's Star Party. And I'm Ruth Carisu. I have a Bachelor of Science in Chemistry from Ursinus College in Pennsylvania. In my professional career, I was an analytical chemist, a nuclear quality engineer, and an entrepreneur. And my claim to space fame is that my company, Solder Mask, supplied components for the International Space Station. So we welcome your questions. Please type them into the question box and we'll answer as many as we can. If we don't get to them all, we'll post the answers on our website along with our video. So let's get the Star Party started. You may have heard us talking before that we're using telescopes from around the world. So Richard, tell our guest about these wonderful telescopes.
I'd be happy to, Ruth. So tonight, we're using telescopes in two different locations, two different observatories run by SLU.com. One observatory is in Chile, and you see a map on the right-hand side of this graphic here, and I've circled where that observatory is located. The other observatory is on the Canary Islands off the western coast of Africa.
Why are these such good locations?
Well, they're both pretty high up. The Chilean observatory is about 7,000 feet in altitude, and the Canary Islands observatory is about 8,000 feet in altitude. It's on the slope of an extinct volcano, and if you look at that picture in the upper left-hand side of this image, you can see that it's well above the clouds of typical weather patterns there in the Canary Islands. The higher up we get, the less atmosphere we're looking through, the less distortion from that atmosphere, the less we have to deal with weather. And also, both of these observatories are far from major metropolitan areas, so they're very dark sites. So they make for great imaging and viewing.
So you're sitting in your office in Lake Forest, and we're using telescopes halfway around the world. How do you manipulate them?
So there are a few companies that have set up remotely controlled telescopes that amateurs and professionals alike can subscribe to. And we have a subscription to this company called SLU. They have a website, SLU.com. Anybody can browse to that website and watch the images that are being collected by their subscribers. Once you sign up for a subscription, you can schedule telescope time. You can schedule specific objects to be imaged at the times that you want. And it's really very easy to do, and it's a great way of getting into astronomy. You're using some very powerful telescopes that normally amateurs wouldn't have access to.
Can you tell us about these telescopes?
Sure can. If we look at this picture here, here's an image of one of the telescopes we're using tonight. This is on the left there, you see the telescope. It's a 14-inch diameter telescope, a 14-inch aperture, which makes it very large for in terms of amateur class of telescopes. It's mounted on a computerized mount there. It's a design called a Schmidt-Cassegrain telescope. And as you can see from the light diagram on the right, the light enters from the lens at the top. That's a corrective lens. It then travels to a convex mirror at the back of the telescope and bounces up to a secondary mirror that's embedded in the corrector lens, and then back through a hole in the primary mirror, that convex mirror. And when the light travels through that hole, it lands on an imager or camera, like the one that's pictured here. This is the one we're actually using tonight, made by Santa Barbara Imager. It's a very large format camera. Attached to it is a filter wheel and 4 colored filters. The software will take approximately a 5-minute image with each color, with each filter, and then combine them together automatically. And what we get is an amazing image from an amazing telescope.
That is fantastic. And I can't wait to see these images of galaxies tonight. So we're talking about galaxies that are far, far away. Mikkel, can you start us off by telling us what is a galaxy?
Well, thank you, Ruth. And thank you, Richard, for the excellent introduction to our instrumentation. It's actually very simple. A galaxy is an accumulation of stars, clouds of gas, and dust, plus a mysterious thing that we call dark matter, all held together by gravity.
Hey, Mikkel, we obviously live in a galaxy, isn't that right?
Yes, indeed, we do. We live in a galaxy called the Milky Way, and it's called that because ancient people looked up on dark nights, back before we had all of the light of civilization. Most of our nights were dark, and they looked up at night and saw what looked like milk splashed across the sky. For those of us who live in cities where the light pollution from just all the stuff that people do, buildings and car headlights and stuff, it hides all but the brightest objects in the night sky. However, if you go someplace where the sky is very dark and allow your eyes to adjust to the faint starlight, you can see the Milky Way, which kind of would look like this picture on the right. It was taken at Joshua Tree National Park out in the California desert east of Los Angeles. And this particular picture was taken at the White Tank Campground, which is in the darkest region of the park. It's nestled among the huge granite boulders that hide most of the glow from the surrounding human activities. It's dark enough there that you get a gorgeous view like this photo, again, of the Milky Way.
I see a bunch of globs of light in this image. You mentioned that it's all held together with gravity. What's up with those globs?
Well, if you give me the next slide, please, Richard. What we see when we look up at night is we are seeing the Milky Way from the inside. Kind of like, I don't know if some of you know the book Harold and the Purple Crayon, but on the picture on the left, Harold is in his bedroom and he's looking out the window. He sees the moon, and maybe he sees some of the other buildings that are facing his window, but he's not really getting a whole picture of the city like we get on the right when we're looking at it from the outside. So the picture on the right is kind of showing us what a city would look like from a person looking outside. So this slide here is kind of like what we would see if we could look at our own Milky Way galaxy on the outside, from the outside. It would look like a giant whirlpool of stars with spiral arms that wrap around a bright, dense center. The spiral arms would be outlined with dark lanes of gas and dust and bright regions of hot young stars. Scientists have been able to create detailed maps of the Milky Way galaxy by measuring the positions and distances to the stars and dust clouds that we can observe in the night sky. Then they use all of that data to make 3D computer models, and that's what this artist conception is based on. Note that it shows where we are in the Milky Way. We live in kind of a far-flung suburb way out on one of the spiral arms. It's a nice, quiet neighborhood far away from most of the action that's happening in the center. Richard, I think you were ready to show us a picture coming in from SLU of another galaxy that looks a lot like our own Milky Way. Is that right?
I do. So here's our first live image of the night. It's a live image of M83.
I'm not sure that we're seeing your image.
Hang on. The telescope went to the next image, but bear with me here. We captured it. We captured it here, and it looked actually really nice. Here we go. Okay. Should be able to bring it up in just a minute. M83 is a spiral, a lot like our own galaxy, isn't that right?
Mm-hmm. Which telescope are we going to be getting the picture from, Richard?
So this one is from Chile 2.
So that's the one that's in South America that you circled on the map.
That's correct. All right, here we go. Now I think I've got it.
And that particular observatory, so first of all, right now it's winter in the southern hemisphere. And secondly, that observatory is built way up high in the, what's it called, the Apacampa Desert. And the air is very dry there. So it's a really, really good place to put telescopes because first of all, it's at very high elevation. So the light doesn't have to go through too much atmosphere. And second of all, the water vapor in our atmosphere absorbs certain wavelengths of light. So if you build telescopes where it's very high and very dry, first of all, you're a lot less likely to have cloudy nights. And secondly, you get just a less filtered, the starlight doesn't get filtered out as much coming through.
And that's an amazing picture that we've received.
Oh, there it is. It came in. Woot!
That is beautiful.
Yay. Yes, that is absolutely gorgeous. I didn't see that coming in there for a second. So in this SLU image coming into us from Chile, we're seeing a galaxy called the Southern Pinwheel Galaxy. It also is called the M83 Spiral Galaxy. That's kind of its technical name. But I think you guys can see that it's called, well, first of all, it's a face-on spiral. So we're kind of seeing it like a plate face-on. And it looks like a pinwheel. It's one of the brightest galaxies in the night sky, easily visible with binoculars, if you happen to be in the southern hemisphere. And Richard, can you bring up the next slide and we'll see what M83 looks like in a Hubble image?
Absolutely. So here's what it looks like through Hubble.
Wow.
That's amazing.
Yes. And this is a high resolution composite image that was produced by combining Hubble Space Telescope images along with ground-based observations taken by the Subaru telescope with that has an 8.2 meter, so that's something like 26 feet, optical infrared telescope. And that's at the summit of Mauna Kea in Hawaii. This is a dwarf, M83 is a dwarf spiral galaxy, kind of like a mini version of the Milky Way. It has an estimated 40 billion stars spread out across about 40,000 light years. That's a lot smaller than our own galaxy, which has 100 to 400 billion stars spread out across about 100,000 light years. In this image, we can see the prominent spiral arms that give the galaxy a pinwheel appearance, and you can see reddish, you can see dark dust lanes and bright young blue stars. They're blue because they're very hot. And then you can see the red stars of glowing gas. These reddish dots, they are star-forming regions. And the way they're dotted all along the spiral arms also give the galaxy its other nickname, the Thousand Ruby Galaxy. So that glowing red colors tells us that there's a lot of active star formation happening in this particular galaxy.
Are there other shapes of galaxies, Mikkel?
Well, actually, there are a lot of different galaxies out there, and this animation is showing us one small portion of the sky that's in among these constellations, and it's what's called the Hubble Deep Field image, so it's going deeper and deeper and deeper in one small area of the sky. No one really knows how many galaxies there are out there. Deep field images like this, taken by the Hubble Space Telescope in the 1990s, like the one we're looking at now, led astronomers to estimate that there are between 100 billion and 200 billion galaxies in the universe. But recent reanalyses of the same images, applying new 3D modeling techniques, have upped the estimate, and we now infer the existence of galaxies that the current generation of telescopes cannot see. So because we understand that our telescopes that we have now aren't able to see all of the galaxies that are really out there, astronomers have revised their estimate of the number of galaxies upward by more than a factor of 10. We now think that there might be trillions of galaxies out in the universe.
Well, they look like they're all different shapes. What do we know about galaxy shapes?
Well, if you give me the next slide, perfect. Galaxies come in a couple of basic shapes: ellipticals on the left, spirals kind of in two prongs on the right, and then I'll talk about the irregulars in a bit. The elliptical galaxies are shaped kind of like squashed balls. Spiral galaxies, like the Milky Way and the Southern Pinwheel that we just saw, have spiral arms winding outward from a brightly defined center. In some spiral galaxies, the center is elongated and kind of bar-shaped, as opposed to just being like round. It's kind of bar-shaped, and so we call them barred spirals. But there are a lot of variations on the basics. Edwin Hubble was the first person to classify galaxies this way. His classification, published in 1926, became called the tuning fork diagram because his first drawing looked like a two-pronged fork. Since then, astronomers have added additional classifications to reflect the diversity of galaxy shapes observed with modern telescopes, like they've added the irregular category all the way to the right of the image. To me, that makes the Hubble diagram here look a little more like a spoon than a fork.
It does.
Astronomers are pretty sure that the Milky Way is a giant SBC type, like the one all the way in the bottom right corner.
Richard, do we have another live image coming in from Canary?
I'm checking right now, and we're trying to get an image of M110. I'm seeing, well, I'll share with you what I'm seeing right now. And should start appearing momentarily. I tell you, let me share another image with you while that one's being collected.
While we're looking for that, Mikkel, you mentioned dark matter. So what is it? Is it, if it's dark, we can't see it, can we? How do we know it's there?
Well, that's actually a really good question. And the reason we call it dark matter is because we don't actually know what it is. All we know is that it's dark, meaning it's not shining brightly. That makes it hard to observe in our regular telescopes. But we know it's there because of the gravitational effects it has on the other matter around it. So for instance, we know that there's dark matter in galaxies because when we count up all the stars that we see in the clouds of gas and dust and all of the stuff that we can actually see in electromagnetic light, it's not enough matter to keep the galaxies held together by gravity. If we look at the way they're spinning and we just look at the matter that's there, it would look like it should be flying apart. So we know there's extra matter in there holding it together, but we don't know exactly what it is. So for now, we're just calling it dark matter. So Richard, are we going with this image?
Yeah, it doesn't look like a Canary came through with an M110 image. I'm not sure if it's clouded out or what we're seeing here.
Luckily, we've got this gorgeous image from the Hubble Space Telescope, and it is of M110, which is a dwarf elliptical galaxy. So like the ones on the left-hand side of the tuning fork diagram. Most of the stuff we're seeing, the bright spots we're seeing around it are nearby foreground stars. This galaxy here, it's a dwarf galaxy, and it's comparable in size to the satellite galaxies of our own Milky Way. It's thought to contain about 10 billion stars, and it's about a third of the diameter of the Milky Way. Dwarf ellipticals are quite common in groups and clusters of galaxies and are often satellites of larger galaxies. Indeed, this particular dwarf, M110, orbits around the giant Andromeda spiral galaxy. Elliptical galaxies. Oop, are we getting the? Oh, Richard, go back, please.
Okay.
We're not quite ready to go yet. Up, yeah, there. So.
Oops, it's Centaurus.
Yeah, can we go back to M110, please?
Sure.
Nope, we're still on Cene. Yeah, that's it. What I wanted to show you is if you look very closely, first of all, it's got, most ellipticals are kind of reddish looking, but this one actually has a bright kind of blue-white core. And then if you look at kind of the why do we keep jumping to Cene? It really wants to come look at us.
There we go. I'm sorry.
Okay. We're almost done with this one. If you look at the 7 o'clock and 11 o'clock positions relative to the core, you can see two kind of dark smudges. Those are real. Those are dark clouds of dust, and they're actually star formation regions. So unusually for a dwarf elliptical galaxy, this galaxy is actually forming stars. And we haven't really figured out why M110 is so different from most other ellipticals. Okay, now show us Cene, if that's come in.
Yeah, this is the image we just collected of Cene. It's a beautiful elliptical, isn't it?
Yes, wow. So I'm actually seeing two separate images. What am I looking at there, Richard?
Yeah, one is one of the black and white images, and the other is the color combined image.
Okay, so it's not that we're seeing double, it's just actually showing us, I guess we are seeing double because it's showing us two separate ones.
You remember I mentioned that we collect in four different filters, and then they get combined at the end.
That's really cool to see an example of that like this. Mm-hmm. So here we see in Centaurus A, it's a giant elliptical galaxy, and we kind of see its elliptical shape, but we can clearly see the distinguishing feature of this galaxy, which is a thick, somewhat S-shaped band of dark dust that obscures our view of the galaxy's center. That band has a lot of star formation happening in it, creating hot, young star clusters. And again, that's unusual for an elliptical galaxy. These hot young stars, plus its proximity to Earth, make Centaurus A appear as the fifth brightest galaxy in our night sky. It's easy to observe with binoculars, but you have to be in the southern hemisphere. And this picture is coming into us from Chile, right, Richard?
That's correct.
Yeah. Scientists think that the peculiar appearance of Centaurus A comes from it being the product of a fairly recent collision of two otherwise normal galaxies, resulting in this fantastic jumble of stars and the imposing dust lane. But the really big surprise from Centaurus A comes when you look at it in radio wavelengths. So if you could give me the next slide, please, Richard.
Coming right up.
So what we've got here on the left is an image like the one we just saw from invisible light of Centaurus A. And then the picture on the right is we've taken the visible light and we've added an image taken in radio wavelengths. Seen in radio waves, Centaurus is one of the biggest and brightest objects in the sky, nearly 20 times the apparent size of the full moon. That's because the visible galaxy lies nestled between this pair of giant radio-emitting lobes, and they extend far, far out beyond what we see at the galaxy in visible light wavelengths. The lobes are filled with matter streaming out from jets that are coming outward, racing outward from the galaxy's center. Astronomers estimate that particles near the base of these jets are racing outward at about 1/3 the speed of light.
Hey, Mikkel, what's powering those incredible jets?
Well, astronomers think that all active galaxies, this one's very active with these lobes and the particle jets, astronomers think that all active galaxies, and maybe even all galaxies, have gigantic black holes in their centers. Material falling into the galactic black hole gets accelerated by the black hole's tremendous gravity. If the black hole is rotating, it'll create a magnetic field, kind of like, have you guys seen the diagram of a magnetic field of like a magnet where it's got kind of loops coming out, maybe a bar magnet coming out of the top and the bottom? So the magnetic field can channel energy and particles so that they have to come out from the poles of the rotation, the axis of rotation. And so they kind of all get concentrated and they have to jet out in that direction. Sometimes the resulting energy comes out as radio wave lobes, like here in Centaurus A, that can outshine all of the galaxies, all of the starlight coming from the galaxy, from all of the stars in the galaxy combined. If the galactic black hole's axis of rotation happens to be aligned toward Earth, so that the jets are lined up pointing right at us, then we can look deeper down toward the core and see brightly glowing X-rays and even high energy gamma rays. Scientists have even managed to make a sort of image of the black hole in the center of M87, which is another active galaxy with a huge radio wavelength jet. Oh, great, you've got a picture of it. Fantastic. M87 is another giant elliptical galaxy, and it's got an astonishing phenomena happening in its core. At the center of M87 lurks a humongous black hole whose mass is estimated to be 2.4 billion, with a B, times the mass of our sun. Energy from materials spiraling into the black hole powers a hugely energetic jet that shoots out of M87's core. We can see that jet in the upper right inset. The particles that are coming out at it in that jet their acceleration is so powerful that the particles at the base of the jet are moving at nearly 99% of the speed of light. Scientists have put together a network of 8 ground-based radio telescopes spaced all around the Earth, operating together as if they were one telescope the size of our entire planet. They collected data over more than a decade of super high resolution images of the core of M87. After a lot of data processing to combine those images, astronomers produced the groundbreaking image that we see in the lower inset. This image of M87's black hole is the first time we've ever been able to see into the dark abyss of one of the universe's most mysterious objects. Of course, we're not really seeing the actual black hole. And that's because black holes, the reason we call them black holes, is because they have such strong gravity that nothing, not even light, can escape from them. So what we're actually seeing in this inset image is a shadow that M87's black hole is casting against the bright accretion disk of the matter spiraling into the black hole.
Hey, Mikkel, I've read that the Milky Way is eventually going to merge with another galaxy. Is that correct?
Yes. And if you give me the next slide, we actually have a little animation of the collision that's going to happen in the distant future of our galaxy. This computer simulation depicts the motion of our Milky Way and 2 neighbors in our local group of galaxy, the giant spiral Andromeda and the smaller spiral Triangulum. These 3 galaxies are being pulled together by their mutual gravity. We know from that the Milky Way and Andromeda are circling one another in sort of a death spiral. About 4 billion years from now, they're going to crash right through one another in a head-on collision. The thin disk shapes. Oops, are we stuck? Is it going to go for us? Yay! Well, maybe we'll just have to kind of go through a little
There it
slow.
goes. It's
But we'll
a little
see
jerky.
the collision completely distorts the spiral shapes of the 2 galaxies, and they're going to be irrevocably transformed by that encounter. Eventually, about 6 billion years from now, the 2 galaxies will merge together to form a single giant elliptical galaxy, kind of like Centaurus A. The 3rd galaxy in the animation, Triangulum, will continue to orbit the merged pair through the end of this computer simulation, which ends about 8 billion years in the future. However, billions of years beyond that, it too will collide into the galaxy that was formed from the remnants of the Milky Way and Andromeda. And that collision is going to set off yet another massive transformation.
So what will the Earth's night sky look like after they merge?
Well, can you give me yeah. I thought we were going to get a, nope, we're on the wrong, yeah. Do you have a picture for me, Richard?
This is an image of the Large Magellanic Cloud that we just collected.
Oh, okay. There it goes. Yay. Okay. So this is one of the satellites of the Milky Way galaxy, and it's called, there it is. It's one of about a dozen or so companion galaxies of the Milky Way, and it's the brightest one of the companions. And we call it the Large Magellanic Cloud, again, because it's the biggest and brightest one. And it was also discovered by the 16th century Portuguese navigator, Ferdinand Magellan, on his first circumnavigation of the Earth. The distance to the Large Magellanic Cloud is only about half again the diameter of the Milky Way. So by galactic distance scales, it's really close. It's so close that it covers an enormous area of the sky, about 20 times the width of the full moon. It has an irregular structure with asymmetric kind of stellar arcs. It's kind of hard to see in this one, but it's got an irregular structure. It's got asymmetric stellar arcs and also abundant clouds of gas and dust. I think we've got a Hubble picture of that, right, Richard?
We do.
There it
That's a
goes.
Hubble picture.
Yeah, so in this image, you can see kind of the arc shapes of the, like up here, kind of above the bright center part, we see the arcs of bright stars, and then you see all of the red cloudy spots are star formation. They're clouds of gas and dust in which star formation is happening. And then kind of on the left side of the image and kind of the lower center of the image, you're seeing really hot, bright, young stars. So we know that there's a lot of active star formation regions. Astronomers think that a long time ago, the Large Magellanic Cloud used to be a dwarf spiral galaxy, but it was stripped of its spiral arms and its center became distorted through repeated interactions with the Milky Way galaxy and also with another companion galaxy called the Small Magellanic Cloud. So we've got the large cloud and the small cloud. Because we're looking at the Large Magellanic Cloud from such a close vantage point and it fills up such a big area of the sky, it gives us a hint of what it might look like to live inside of a distorted galaxy. Remember, like Harold looking at the city from his bedroom window inside the city? So our vista here, what we're seeing of the Large Magellanic Cloud, is an example of what might stretch across the Earth's whole night sky billions of years from now. So Richard, I think you've got a really special last image from us coming down from Chile, maybe?
This one's coming from the Canary Islands. And let's see if we can get this stored and opened up. Here we go. This is the Andromeda Galaxy.
So this is a galaxy that some of our audience may already be familiar with. And if you've ever been to a star party, you know, you may even have had a chance to see it. It is from the SCT Telescope. And which one, Richard?
This is Canary 4.
Okay. It's a spectacular image of the Andromeda Galaxy. Andromeda is the nearest galaxy that isn't one of the Milky Way's satellites. It appears in the southern hemisphere. If you're looking on a dark night, it's bright enough to be seen with the naked eye. And in fact, it is the farthest away naked eye object that you can see with your unaided eye. On a very dark, clear night, it would look like a hazy smudge, slightly wider than the full moon. Andromeda is a spiral galaxy shaped similarly to our own Milky Way, but it's a spiral as opposed to a barred spiral. It's about twice as big as our Milky Way and contains about twice as many stars, maybe as many as 1 billion. Andromeda is in a fairly quiescent phase right now, but we think that as recently as 100 million years ago, well, that's what counts as recent in galaxy time, it went through a burst of active star formation. And that was set off when Andromeda swallowed up one of its satellite galaxies that ventured too close. Our next slide, and it's the last one I have for you this evening, is a Hubble image of the Andromeda Galaxy. So you can see the Large Magellanic, you can see 2 of its satellite galaxies, M110, which was the dwarf elliptical that we saw earlier tonight, is up in the upper right corner. And then there's another satellite galaxy that appears a little smaller, just down below the main bright part of Andromeda. The upper one, again, is the dwarf elliptical galaxy M110 that we were looking at earlier this evening. You can easily see the clouds of bright stars, these blue stars down at the bottom, and around it are young stars. You see the dark reddish, a little bit reddish looking lanes of dust. And Andromeda reminds us that galaxies are, while they're beautiful, they are not exactly everlasting jeweled islands floating in the serene cosmic sea. We observe galaxies shooting out jets from massive black holes in their cores, like Centaurus A and M87. We see them interacting with one another. We see them having swallowed their satellites, and sometimes even crashing together in huge collections. So we see that the cosmos is an exciting and dynamic place with lots of interesting stuff going on. And I thank you all so much. That wraps up our presentation. So I thank you all so much for joining me in a tour of the heavens this weekend.
Well, we have a couple of questions. First of all, why does the center of the galaxy look brighter?
Well, that's because the stars are more concentrated there. So when you're looking at a given amount of stretch of the sky, there's just a lot more stars kind of all crammed together in that stretch of sky if you're looking at the center of the galaxy than if you're looking out away from the center. It's like having a whole lot of candles crowded together on a table as opposed to just having one or two candles.
So you talked about a black hole in the center of the other galaxy that we saw. Does the Milky Way have a black hole in its center as well?
Yes, indeed it does. And we think that the black hole in the center of the Milky Way has a mass equivalent to a few million stars. And we know that there is a black hole, and we can get an estimate of its mass by looking at the paths of stars that are close to the center of the Milky Way, and kind of the way they're in orbit around that black hole. The center of our Milky Way can be seen from the southern hemisphere in the constellation of Sagittarius. And if you ever get a chance to go down to the center, if you ever get a chance to go down to the southern hemisphere, there's a lot of really cool astronomy stuff to look at down there, because again, that's the direction where we're looking at a bunch of interesting stuff that's inward from us in the Milky Way galaxy.
So is the black hole in the center of the Milky Way something we need to worry about? Is that going to swallow up the Earth?
No, because remember the image that I showed you of the artist's conception of the map of the Milky Way? We're like way far out in the burbs. So even if there's something going on in the center of the city, it's not really going to affect us because we're way far out in a quiet neighborhood.
Okay, well, that's good to hear. I'm checking the question box here, and let me see what we have. And I'm not able to pull up the entire question.
You double click on it, it'll open.
Okay. This is Larry Schumann, a volunteer, and you were talking about two black stars colliding.
Two black holes?
He has black star, but I think it's black holes. Last week, in either the LA Times or the Daily News was a big article in the collision of two big black holes occurring in a galaxy on the edge of the universe.
Mm-hmm. So there's a project that's been going on for quite a number of years called LIGO. and it's the trying to remember what the laser interferometer gravity observatory, LIGO. And that is an instrument that's been set up that measures, it's really cool. They've got two heavy masses, because remember, gravity interacts with mass. So they've got two masses very, very, very precisely suspended with a laser going in between them. And they actually have two going this direction and going this direction. And what they're looking for is they're looking for gravity waves. And when remember, gravity waves work by distorting the actual fabric of space, just like waves in the ocean kind of distort the surface of the ocean and make the water move around. So when a gravity wave comes through, it makes those two really big, massive blocks, or the three of them, move relative to each other. And using the lasers, they can measure the positions of them super, 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 super precisely. And so when there's an event like two black holes that spiral into each other and coalesce, that forms it's kind of like dropping a rock in a pond of still water, and it creates gravity waves that come out from the center of that event. And when they pass through this LIGO detector, they can detect the effect that wave has on the positions of the block, and they can detect the gravity wave going by. There's a really smart physicists that are really good at math have come up with models of what it would look like if two really massive black holes, or black holes of different masses, spiraled into each other and coalesce. And it makes kind of a chirping signal. They call it a chirp because it starts big and it gets smaller. So I guess to their detector, it's kind of like a sound wave from a chirp. And they detected an event like that. I believe it was some 18 months ago, but it took them 18 months to process the data, and they just released the data last week. And what fits the observed signal that they saw best is the collision and coalescence of two black holes. And I believe one's about 60 solar masses, 65 maybe, and the other's around 100 solar masses. So the scientists are very, very excited about that. And all of this, the existence of gravity waves, and every time they see an event like that, it gives them another data point to confirm their models. And so the theorists get really excited about it, and that's why it gets all over the news.
Richard, there's a question here for you. Were the SLU pictures astrophotography or what your eye would see at the eyepiece?
So some of the images that we shared, the live images, were astrophotography, but they're collected over about 4 or 5 minutes using each filter. So it's better than what your eye would be able to see. But our eyes are pretty good. They have a large linear dynamic range, and for example, that image that Mikkel shared with us of the Joshua Tree image with the Milky Way in the background. When we look up in the sky from Joshua Tree, we see quite a bit of the Milky Way if it's nice and dark. Not as much as that long exposure image, but quite a bit of it. So your eyes are pretty good. Not as good as a camera, but they're pretty good.
Yeah, and like the image of the Andromeda Galaxy from Hubble, that's actually a composite image that was taken in ultraviolet wavelengths, which are shorter wavelengths, a little bit more energetic than our eye can see, regular visible light, and then also infrared light, which is a little bit longer wavelength than our eye can see. So it's actually showing a bit more than our eye can see, but gosh, it's a pretty picture. And actually, if you go, if you're lucky enough to go down to the southern hemisphere, even with a good pair of binoculars, if you're patient, your eyes have a really good dynamic range response. So if you're patient and you let your eyes dark adjust, and you really just are patient in watching through the binoculars, whatever, you can get some really stunning impressions of some of these nearby galaxies.
And here's another question for you, Mikkel. Can you explain the galaxy spin? Do they spin in 2 or 3 dimensions and counter or counterclockwise?
So the direction, it's random. And like these spiral galaxies, the reason they're spirals, have you guys seen that trick with the guy with, he's got the rod and he's got the plate spinning on a rod? Yes. And he's kind of got the rod in the center of the plate and it's spinning around. That's kind of what's happening with these spiral galaxies. So it's like a whirlpool and it's spinning in the direction that it looks like with the spiral arms. And with the elliptical galaxies, if they're like a squashed ball, it's a little bit squashed. It's not a perfectly round ball, but it's a little bit squashed because they're spinning, and the axis around which they're spinning is usually the one where they're squashed on, and they're a little bit squashed because they are spinning.
And another question here, can you explain how we know how far away a star or galaxy is from us? And then redshift.
That is a great question. And we actually have a lot of different methods for telling how far away something is. And we're going to have an entire solar head star party to talk about that. I believe, is that the one we're doing in March, Richard?
Yes, it is. It's actually February. It's actually February.
February. Are you sure? I thought it was Women's History.
Let me double check. I think
maybe it is February. I think I've got. Yes, but a large portion of the work done on determining the distance scales and figuring out how to measure distances to object was actually March, correct?
Yes.
Yeah, a large portion of the work done on figuring out how to measure distance to astronomical objects was done by women astronomers. And so we'll be doing an entire star party based on that to celebrate Women's History Month in March. So I'm gonna kick that one down the road and invite you all to join us for a special Women's History Month star party.
Sounds like a plan. I think that wraps it up for tonight. I don't see any more questions here in chat or in the question box. I want to thank you all, on behalf of Science Heads, for joining us. Please check out our website at scienceheads.org. There's a lot of information, and you can volunteer to be part of this team. The video will be posted there, as well as answers to the questions. There's information up on your screen now about the telescopes and about NASA. They have a tremendous wealth of resources that you can look at and learn more about galaxies.
And see a ton of pretty pictures too.
Yes, yes. So our next one is going to be on beautiful star clusters, and we're not talking about the latest item in Hollywood. Globs and open clusters on Friday, October 2nd. So we invite you to join us. We thank you for your participation tonight. Have a wonderful weekend and be safe.
Thank you all for joining us.
Good night.